Good morning. We will continue our discussion with rotational vibrational spectroscopy. In the last videos, we have discussed about the rotational vibrational spectrum of a diatomic vibrating rotator, and we derived an expression delta EJV, uh, delta E associated with the rotation and vibrational change in a vibrating rotator as delta EJV is equal to omega bar 0 plus 2bm centimeter raised to minus 1. And we have also seen that a rotational vibrational spectrum of a diatomic molecule consists of p and r p and r branches and the lines are equal consists of p and r branches, and the spectral lines are separated by and spectral lines are equally separated or equally spaced with a separation of 2b. And this is a case of an idealized rotational vibrational spectrum. But if you observe the rotational vibrational spectrum of a real molecule, say HCl, which is given in this slide, you will observe that the P and R branches are not equally spaced as expected. As expected, and if you observe it, you can see that the spectral lines crowd more closely together with increasing M on the R branch side, and the spectral lines become more widely spaced as M increases on the P branch side. And why this is happening? This is because of the interaction between rotation and the vibration motion. In the last session, when you derived this expression, for deriving this expression, we used what is known as a Born-Oppenheimer approximation. And according to Born-Oppenheimer approximation, a diatomic vibrating molecule can execute both rotation and vibrational motion quite independent of each other. But this is not the real situation. We know that a molecule undergoes many vibrations during one rotational period, and the bond length changes, and it is evident that the bond length changes during the vibration. And if the bond length changes during vibration, it means that the bond length changes continuously during rotation. And you know that the rotational constant B is inversely proportional to the moment of inertia. It implies that it is inversely related to the R square. That is, it is inversely related to the bond length. So if the bond length changes continuously during rotation, it means that the B is also, that is the rotational constant, is also changing. And when a molecule undergo a vibrational transition from 0 to 1, we know that R equilibrium, the bond amplitude of vibration increases and R value changes. This implies that the rotational constant B varies with the vibrational quantum number. Since R value increases with vibrational energy, B will be smaller in the upper vibrational state when compared in the upper vibrational state than in the lower vibrational state. This is because R value increases when molecule undergo transition from the lower vibrational state to the higher vibrational state, and as R value increases, B value decreases, which implies that the B is smaller in upper vibrational state than in the lower vibrational state. So you have to consider this result, or you have to consider this factor when you derive the delta E for when you derive the expression for delta E for a diatomic molecule exhibiting simultaneously both rotational and vibrational transition. So in this equation, considering only V is equal to 0 to V is equal to 1 transition, delta EJV is equal to EJ dash into V is equal to V minus EJ dash V is equal to 1 minus EJ double dash V is equal to 0. You will get is equal to omega bar 0 plus B1 J dash into J dash plus 1 minus B0 J double dash into J double dash plus 1. And this is the lower rotation energy associated with the lower vibrational state, and this is the rotation energy associated with the upper vibrational state. So for our branch, delta J is equal to +1, and we know that J dash then will be equal to J double dash plus 1. So in the expression delta E JV omega bar 0 plus B1 J dash into J dash plus 1 minus B0 J double dash into J double dash plus 1, you will apply this expression for J dash. Hopefully, I hope that you're noting down this, you're simultaneously deriving this equation with me. Otherwise, you'll find it difficult to follow here. So we are substituting the value J dash. We are substituting the value of J dash in this equation, and you will get another expression omega bar 0 plus B1 J double dash plus 1 into J double dash plus 2 minus B0 J dash into J double dash plus 1. So taking the factor J double dash 1 as common, you will get omega bar 0 plus J double dash plus 1 into into J double dash plus 2 minus B0 J double dash. And now we are going to expand this term in this bracket. Omega bar 0 plus J double dash plus 1 into B1 J double dash plus 2 B1 minus B0 J double dash. And in the next step, you are going to add and subtract B0 from this expression. Just you're manipulating this equation. You're going to add and subtract B0, and you will get omega bar 0 plus J double dash plus 1 into B1 J double dash plus 2B1 minus B0 J double dash plus B0 minus B0. In the next step, you're going to write 2B1 as B1 plus B1. Therefore, you will get an expression like omega bar 0 plus J double dash plus 1 into B1 J double dash plus B1 minus B0 J double dash plus B0 minus B0. And now what you're going to do is that you can see that B1 J double dash, you're going to take these two terms together, and you can write B1 plus B0 as one term, and you're going to rearrange the terms into B1 minus B0. Omega bar 0 is equal to J dash plus 1 into J double dash into B1 minus B0 plus B1 plus B0 plus B1 minus B0. So in the next step, you're going to do you're going to take this B1 minus B0 terms as common. Therefore, you'll get omega bar 0 plus J double dash plus 1 into B1 minus B0 into J double dash plus 1 plus B1 plus B0. And therefore, you'll get finally the equation as omega bar 0 plus B1 plus B0 J double dash plus 1 plus J double dash plus 1 the whole square into B1 minus B0 centimeter raised to minus 1. And we know that for pre-branch, delta J is equal to minus 1. And using this expression, J double dash plus is equal to J dash plus 1. And you can do it as a homework. You can by using this kind of simple mathematics, you can derive delta EJV for a P branch is equal to omega bar 0 minus B1 plus B0 into J dash plus 1 plus J dash plus 1 the whole square into B1 minus B0 centimeter raised to minus 1. So combining the two equations, what you can write is that delta EJV is equal to omega bar 0 plus B1 plus B0. Instead of J double dash plus 1 and J double dash plus 1 and J dash plus 1, we will use the term M. And here you will write M square into B1 minus B0. And this M value will be positive for R branch and negative for P branch. And M square, you know that it's a square, so it will be always, this M square will always be a positive value. So if you look at this closely, you will get this expression as delta EJV is equal to omega bar 0. And if you remember, omega bar 0 is actually equal to omega bar E into 1 minus 2 chi E centimeter raised to minus 1. I hope that you remember that point. And B1 plus B0 M. So this value can be positive or negative depending. If this value can be positive, it is R branch, and this value can be B1 plus B0 M can be negative if it is a P branch. And if you look at this value M square B1 minus B0, we know that B1 is the rotational constant associated with the upper vibrational state, and B0 is the rotational constant associated with the lower vibrational state. And we know that B1 will be always less than B0. Therefore, the term B1 minus B0 is always negative irrespective of the sign of M. So this can be positive or negative depending on the P branch, and this is always negative if it is for both P branch and R branch. So what is going to happen is that in the rotational vibrational spectrum or in the root vibrational spectrum, the lines become more closely packed with increasing M on the R branch side, and the spectral lines are becoming more widely spaced as M increases on the P branch side. So what is happening? What is essentially happening is that in case of a real diatomic vibrating rotator, it involves a breakdown of Born-Oppenheimer approximation. And you can use this, you have to use this expression, or you have to use this equation to account for the real, you have to account for the spectrum of a real diatomic, to account the rotation vibrational spectrum of a real vibrating diatomic molecule. That means you have you should you should not, you are considering that the situation as a breakdown of Born-Oppenheimer approximation, or you can say that the Born-Oppenheimer approximation is no longer valid, or you cannot use Born-Oppenheimer approximation to derive the expression for a to derive an expression or to account the observation of a P branch, to account the observation of a to account the spectrum of a real diatomic vibrating rotator. Here you are to derive this expression, you are not using the Born-Oppenheimer approximation. Here you can see that the B rotational constant varies with the vibration energy. It implies that the rotation motion is interacting with the vibrational motion. So the Born-Oppenheimer approximation is no longer valid. And this is a real situation where you can see that the breakdown of Born-Oppenheimer approximation occurs. Hope you have understood the video, and this is all about the rotational vibrational spectroscopy of a diatomic molecule. In the next video series, we will discuss about the vibrations of a polyatomic molecule. Thank you.